Most people think they understand electricity because they can flip a switch. I spent decades working with electrical current, building systems, designing circuits, watching thousands of experiments succeed and fail. People see the light come on and think electricity flows like water through a pipe. They imagine little particles racing from the power plant to their home at incredible speed. This is wrong. When I first grasped what electricity actually is, it changed everything I thought I knew about the work I'd been doing. The current doesn't rush anywhere. The energy moves, but not the way anyone pictures it. The electrons barely crawl. What we call electrical flow is something far more elegant, far more surprising than the simple picture we carry in our minds. This misunderstanding shapes how people think about every electrical device they touch. Before we continue, take a moment to notice where you're listening from, and if this story stays with you, you're welcome to return tomorrow for what comes next. The morning I held my first successful incandescent bulb, October 21st, 1879, I thought I understood what I had accomplished. The carbon filament glowed steadily in its glass vacuum, casting warm light across my Menlo Park laboratory. I had solved the problem of electric illumination, or so I believed. The bulb sat in my palm, still warm from its successful test. Inside that glass sphere, I knew electricity was flowing through the carbon thread, heating it until it glowed. Simple enough. Current enters through one wire, passes through the filament, exits through the other wire, the same way water flows through a garden hose. Every electrical engineer of my generation understood it this way. But something nagged at me as I examined that bulb. The filament had responded instantly when I closed the circuit. Not after a delay, not gradually. Instantly. As if the electrical effect had traveled the length of wire from my generator to the bulb faster than I could perceive. This troubled me more than I initially admitted. My education in electrical matters began with telegraphy in my youth. Samuel Morse's system had taught me that electrical signals could travel great distances through copper wire. When an operator pressed a key in New York, the signal appeared almost immediately in Boston. We measured the speed and found it remarkable, though we never questioned the mechanism itself. Working as a telegraph operator in my 20s, I learned to think of electrical current as something substantial moving through the wire. My supervisors explained it simply. Close the circuit, current flows, the signal travels. Open the circuit, current stops, signal ends. The copper wire was like a pipe, the electrical current like water rushing through it. This understanding served me well through my early inventions. The phonograph, the stock ticker, the incandescent lamp itself. I built circuits, connected components, observed results. When current flowed, devices operated. When current stopped, they didn't. The water through pipes model never failed me practically. Michael Faraday's work had fascinated me since I first encountered his writings in the 1860s. His copper disc generator, spinning between magnetic poles, produced electrical current without any apparent connection to a power source. The mechanical motion somehow became electrical energy. I understood this phenomenon well enough to use it, building my own generators based on his principles. Yet even then, questions lingered. When Faraday spun his copper disc, electrical current appeared immediately at the collection brushes, not after the copper atoms had time to physically move from one side of the disc to the other. Immediately, the effect seemed to outpace any conceivable physical process within the copper itself. I built countless variations of Faraday's generator at Menlo Park. Each one demonstrated the same mysterious instantaneous response. Spin the disc, current appears. Stop the disc, current ceases. The timing suggested something more sophisticated than simple physical movement of electrical matter through the metal. My assistants and I would debate this during long evenings in the laboratory. Charles Batchelor, my chief machinist, maintained the conventional view. Current flows like water, Mr. Edison. Fast water, but water nonetheless. He could point to clear evidence, increase the voltage, more current flows. Restrict the wire size, less current flows. The hydraulic analogy explained everything we observed. But Francis Upton, my mathematician, occasionally raised troubling questions. He had studied at Princeton and understood the newer theories emerging from European universities. Mr. Edison, he would say, the mathematics suggest something more complex than simple flow. Maxwell's equations describe electrical phenomena as field effects, not material transport. I dismissed such theoretical concerns at the time. My business was practical invention, not mathematical abstraction. If the water flow model helped me design working devices, why complicate matters with exotic theories? I could make electricity do useful work. That seemed sufficient. The incandescent lamp project forced me to think more carefully about electrical behavior. Creating a stable, long-lasting filament required precise control of electrical current. Too much current. The filament burned out quickly. Too little, insufficient light output. I needed to understand exactly what was happening inside that thin carbon thread. Through hundreds of experiments, I learned that the filament's temperature depended directly on the electrical current passing through it. This relationship followed predictable patterns that allowed me to calculate optimal filament designs, yet the underlying mechanism remained mysterious. Why did electrical current heat the filament? What was actually occurring at the atomic level? My practical work continued successfully without answering these deeper questions. I developed improved generators, better distribution systems, more efficient lamps. The water flow model guided all these innovations effectively. Current flowed from generators through wires to devices, accomplishing useful work along the way. But the instantaneous response problem never left my mind completely. When I closed a circuit in my laboratory, devices 100 feet away responded immediately. Not after a delay corresponding to some material traveling that distance. Immediately. This suggested that electrical effects propagated much faster than any conceivable physical process. The conventional explanation involved extremely rapid movement of electrical matter through the wire. Perhaps electrical particles moved at tremendous speeds, fast enough to seem instantaneous over short distances. This satisfied most engineers and inventors of my era. We didn't need to understand the exact mechanism, only to harness the effect. Yet careful observation revealed inconsistencies in this simple picture. Heavy copper wires carried more current than thin ones, as expected if current involved physical flow. But the relationship between wire thickness and current capacity didn't match what we would expect from a liquid flowing through pipes of different sizes. Something else was happening. I began keeping detailed notes about these electrical anomalies in my laboratory notebooks, small discrepancies between theoretical expectations and practical observations. Nothing that prevented successful invention, but enough to suggest our fundamental understanding might be incomplete. The successful demonstration of my complete electrical lighting system in 1879 brought congratulations from colleagues and investors. I had proven that electricity could replace gas lighting economically and safely. The Pearl Street Power Station would soon bring electric illumination to Lower Manhattan. My work was bearing fruit. But success in practical application only intensified my curiosity about the underlying mechanisms. How exactly did electrical energy travel from my generators to the lamps? What happened inside the copper wires during this process? Why did the system respond instantaneously despite the apparent complexity of the energy transfer? These questions would not leave me alone. I had built a successful electrical business based on incomplete understanding. The devices worked, the customers were satisfied, the investors were happy, yet I knew I was missing something fundamental about the nature of electrical phenomena. That October evening, holding my first successful incandescent bulb, I made a decision. I would investigate electrical behavior more systematically, beyond the practical requirements of invention. I would try to understand what electricity actually was, not merely how to use it effectively. This decision would lead me into territory that challenged everything I thought I knew about electrical current and energy transfer. What I discovered would transform my understanding of every electrical device I had ever built. The experiment that shattered my understanding began with the simplest possible setup. A length of copper wire, 18 inches long, with small scratches marked every inch along its surface. I had made these marks myself with a fine blade, creating reference points for what I hoped would be a definitive measurement. Winter of 1880 brought unusually cold weather to Menlo Park. The laboratory felt drafty despite our best efforts to seal the windows, but cold air helped with precision measurements, keeping the equipment stable and my hands steady. I needed both for what I was attempting. Francis Upton had suggested this experiment during one of our evening discussions. If electrical current truly flows like water through the wire, he had said, we should be able to measure the speed of that flow directly, mark the wire, introduce some kind of tracer, observe how long it takes to travel from one mark to another. The concept seemed straightforward enough. I would create a measurable disturbance in the electrical current and time its progress along the marked wire. If current flowed like water, this disturbance should move at a speed corresponding to the physical motion of electrical matter through the copper. I connected one end of the marked wire to my most sensitive galvanometer, an instrument capable of detecting tiny changes in electrical current. The other end connected to a simple circuit that I could interrupt and restore at will. By opening and closing this circuit rapidly, I could create a pulse of current and observe its arrival at the galvanometer. The first attempts yielded confusing results. When I closed the circuit, the galvanometer responded immediately. When I opened it, the response ceased immediately, no measurable delay, even with 18 inches of wire between the switch and the detecting instrument. This suggested either that my timing methods were inadequate or that electrical effects traveled much faster than I had anticipated. I refined the experiment, extending the wire to 6 feet, then 12 feet, then 30 feet. Each time the same result. Instantaneous response. The galvanometer needle moved the moment I operated the switch, regardless of the wire length. This was puzzling but not yet revolutionary. Perhaps electrical particles simply moved faster than I could measure with available instruments. Charles Batchelor proposed a different approach. Instead of timing the current pulse, he suggested, why not try to observe the actual movement of electrical matter within the wire itself? If current flows like water, something physical must be moving from one end to the other. This idea led to more sophisticated experiments. I prepared several identical copper wires and subjected them to carefully controlled electrical currents. After various durations of current flow, I would remove sections of wire and examine them under magnification, looking for any physical evidence of material transport. The microscopic examination revealed nothing unusual. Wire that had carried heavy electrical current for hours appeared identical to wire that had never been electrified. No displacement of copper atoms, no directional reorganization of the metal structure, no physical trace of anything having flowed through the material. This absence of physical evidence troubled me more than I initially admitted to my assistants. If electrical current involved the movement of substantial quantities of matter through the wire, some trace should remain. The copper atoms should show signs of disturbance, some pattern indicating the direction and magnitude of the flow. Yet I found nothing. The wire looked exactly the same before and after conducting electricity. This suggested either that electrical current involved incredibly small amounts of matter moving through the wire, or that our fundamental conception of electrical current was somehow incorrect. I decided to attempt a more direct measurement of particle motion within an electrified wire. Using techniques borrowed from my work with magnetic field mapping, I prepared a series of experimental setups designed to detect any physical movement of material within copper conductors. The most promising approach involved creating a magnetic field around the test wire and observing any changes in that field as electrical current flowed. If substantial amounts of matter were moving through the wire, this motion should create detectable magnetic effects that I could measure precisely. After weeks of careful experimentation, the results were startling. The magnetic measurements indicated that any physical motion of particles within the wire was extraordinarily slow, far too slow to account for the instantaneous electrical effects I routinely observed in my circuits. I repeated these measurements dozens of times, using different wire materials, various current levels, and increasingly sophisticated detection methods. Every measurement pointed to the same conclusion. Whatever was physically moving through the wire moved at a crawl, mere millimeters per second, under typical operating conditions. This discovery created a profound contradiction in my understanding. Electrical effects propagated through circuits instantaneously, yet the physical motion within the wires proceeded at glacial speed. These two observations seemed mutually exclusive. How could electricity work instantly if its physical components moved so slowly? I spent sleepless nights pondering this contradiction. My practical experience with electrical devices was extensive and reliable. Circuits responded immediately when closed, stopped immediately when opened. This immediate response was essential to the operation of every electrical device I had ever built. Yet the careful measurements clearly show that physical particle motion within wires was extremely slow. If electrical current depended on particles traveling from source to destination, then electrical devices should respond with delays corresponding to this slow motion. But they didn't. The implications were unsettling. Either my measurements were systematically wrong, or my fundamental understanding of electrical current was deeply flawed. I trusted my experimental technique, developed through years of careful work. The measurements seemed reliable. This left the uncomfortable possibility that electrical current was not what I had always believed it to be. Francis Upton found these results fascinating rather than troubling. His mathematical background had exposed him to newer theoretical work from European scientists. Mr. Edison, he said, these measurements align with some recent theoretical predictions. Perhaps electrical current is not primarily about particle motion through the wire. I asked him to explain what alternative he had in mind. His answer introduced concepts that challenged everything I thought I knew about electrical phenomena. Consider, he said, that electrical energy might propagate as a field effect around the wire, rather than as particle motion through the wire. The physical particles within the conductor might serve primarily as a medium for field propagation, not as the carriers of electrical energy themselves. This suggestion seemed almost mystical to me initially. Field effects were abstract mathematical concepts. I worked with tangible mechanical systems, generators, wires, lamps, switches, physical objects that I could see, touch, and measure directly. The idea that invisible fields might be more important than these physical components was difficult to accept. But the experimental evidence was becoming harder to ignore. Physical particle motion was too slow to explain electrical behavior. Something else must be responsible for the instantaneous propagation of electrical effects through circuits. I began researching the theoretical work Upton had mentioned. James Clerk Maxwell's electromagnetic field theory, published in the 1860s, provided mathematical descriptions of electrical phenomena that seemed to match my experimental observations. According to Maxwell, electrical and magnetic effects propagated as waves in an invisible medium, traveling at enormous speeds. Maxwell's equations predicted that electromagnetic waves should travel at approximately 300 million meters per second. This speed was fast enough to seem instantaneous over the distances involved in typical electrical circuits. If Maxwell was correct, then electrical energy propagated as field waves, not as particle motion. This theoretical framework offered a potential resolution to my experimental contradictions. Electrical effects could propagate instantly through electromagnetic field waves while physical particles within the conductors moved slowly. Field carried the energy. The particles merely facilitated field propagation. But accepting this explanation required abandoning the intuitive water flow model that had guided all my previous work with electricity. Instead of current flowing through wires like water through pipes, I would need to think in terms of invisible field waves propagating around and through the circuit components. The transition from mechanical to field thinking was not easy for someone trained in practical invention. Fields were mathematical abstractions, not tangible objects. How could I design circuits and devices based on invisible, intangible phenomena that I could only detect through their effects? Yet the experimental evidence was compelling. The measurements of particle motion were consistent and repeatable. The theoretical predictions matched the observed behavior of electrical systems. The field model explained phenomena that the particle model could not. I realized that my investigation had reached a critical point. I could either dismiss these findings and continue working with familiar but apparently incorrect concepts, or I could accept the evidence and begin learning to think about electricity in fundamentally different terms. The choice would determine not only my future understanding of electrical phenomena, but also the direction of all my subsequent work with electrical systems. Everything I planned to build depended on how electricity actually worked. The weeks following my measurements brought a peculiar kind of intellectual vertigo. I would stand in my laboratory, surrounded by generators, switches, and circuits that I had designed and built, yet suddenly they seemed like mysterious artifacts from an alien civilization. Everything worked exactly as before, but I no longer understood why. James Clerk Maxwell's manuscript pages lay scattered across my desk, covered with equations that Francis Upton had copied from the original publications. The mathematics was dense, filled with symbols and operators that challenged my practical engineering mind. But hidden within those equations was a description of reality that matched my experimental observations far better than anything I had previously encountered. Maxwell described electrical and magnetic phenomena as manifestations of a single electromagnetic field that permeated all of space. This field could support waves that propagated at enormous speed, carrying energy from one location to another without requiring any physical substance to travel the intervening distance. The concept was revolutionary and deeply unsettling. According to Maxwell's theory, when I closed a switch in an electrical circuit, I was not starting a flow of particles through the wires. Instead, I was creating a disturbance in the electromagnetic field surrounding the circuit. This disturbance propagated outward at nearly the speed of light, carrying energy to distant parts of the circuit almost instantaneously. The physical particles within the wires played a supporting role, facilitating the field propagation but not carrying the energy themselves. The electrons moved slowly, as my measurements had shown, but the electromagnetic field moved rapidly, delivering energy where it was needed at speeds that appeared instantaneous over practical distances. This field-based understanding explained many electrical phenomena that had puzzled me over the years. Why did circuits respond instantly regardless of their physical size? Because electromagnetic field propagation was not limited by the slow motion of particles within conductors. Why did electrical energy seem to appear simultaneously throughout a circuit when power was applied? Because field effects propagated much faster than any mechanical process. Yet, accepting this explanation created profound difficulties for my approach to electrical engineering. I had built my career on mechanical intuition, understanding devices in terms of physical processes that I could visualize and manipulate directly. The electromagnetic field was invisible, intangible, and mathematically abstract. How could I design practical devices based on something I could never see or touch? My existing electrical systems continued to operate successfully, but I no longer trusted my understanding of their operation. Every time I observed a light bulb illuminate instantly when I closed a switch, I was reminded that the underlying mechanism was far more sophisticated than I had realized. The simple mental model that had guided my inventions for decades was fundamentally incorrect. This created a crisis of confidence that affected all aspects of my work. When investors asked me to explain how my electrical systems functioned, I found myself using language that I no longer believed. Current flows through the circuit. powering the devices, I would say, knowing that this description was at best misleading and at worst completely wrong. The problem became more acute when I attempted to design improvements to my electrical systems. Previously, I had relied on mechanical analogies to guide my innovations. If I wanted more current capacity, I made the conductors larger, like increasing the diameter of a water pipe. If I wanted to distribute power more efficiently, I arranged the circuit like a branching network of pipes and valves. These mechanical analogies had worked well enough for crude approximations, but they failed when I needed precise control over electrical behavior. The field-based reality was more complex and subtle than simple hydraulic models could capture. To design truly optimal electrical systems, I would need to think in terms of field propagation, impedance matching, and electromagnetic wave behavior. The challenge was compounded by the fact that most of my colleagues and competitors continued to work with the traditional particle flow model. When I attended meetings of electrical engineers, everyone spoke confidently about current flowing through circuits. As if this description was obviously correct, I found myself unable to participate naturally in these conversations, knowing that the fundamental assumptions were wrong. Charles Batchelor noticed my growing unease with standard electrical terminology. "You've been unusually quiet during the technical discussions, Mr. Edison. Is something troubling you about the generator designs?" I struggled to explain my dilemma without sounding like I had lost confidence in my own expertise. How could I tell my most trusted assistant that I no longer understood the devices we built together every day? How could I admit that our shared vocabulary for describing electrical phenomena was based on misconceptions? "Charles," I finally said, "what if electrical current doesn't flow through wires the way we've always assumed? What if the energy travels by some other mechanism that we've never properly considered?" His response was predictably skeptical. "Mr. Edison, our devices work perfectly well based on current understanding. The Pearl Street station delivers power reliably to hundreds of customers. Our lighting systems operate exactly as designed. Why complicate matters with exotic theories that don't improve practical results?" This practical argument was difficult to refute. My electrical systems were indeed successful by any reasonable measure. Customers were satisfied, investors were profitable, and competitors were copying my designs. From a business perspective, deeper theoretical understanding seemed unnecessary and potentially distracting. But I could not ignore what I had learned through careful measurement and analysis. The conventional description of electrical current was demonstrably wrong, regardless of whether this wrongness affected practical applications. As an inventor and engineer, I felt obligated to understand the true mechanisms underlying my creations. The conflict between practical success and theoretical accuracy created persistent tension in daily work. I continued building and selling electrical devices based on design principles that I knew were incomplete. My customers received reliable products that met their needs, but I was troubled by the gap between apparent functionality and genuine understanding. Francis Upton proved more receptive to the implications of field theory for electrical engineering. His mathematical background allowed him to work directly with Maxwell's equations, extracting practical insights that were not obvious from mechanical analogies. "Mr. Edison," he said, "the field equations suggest optimization strategies that the hydraulic model cannot reveal. We might be able to improve our system significantly by designing for field propagation rather than particle flow." This possibility excited me despite my discomfort with abstract mathematical approaches. If field theory could lead to better electrical devices, then the theoretical investment would justify itself through practical improvements. I asked Upton to identify specific areas where field-based design might outperform traditional methods. His analysis revealed several promising opportunities. Power transmission efficiency could be improved by optimizing the electromagnetic field configuration around conductors. Circuit response could be made more predictable by accounting for field propagation delays in large systems. Device reliability could be enhanced by reducing unwanted electromagnetic interactions between system components. These potential improvements were significant enough to warrant serious investigation, but pursuing them would require abandoning familiar design methods in favor of field-based approaches that I did not yet fully understand. The transition would be risky, time-consuming, and potentially expensive. Moreover, explaining field-based designs to customers, investors, and competitors would be challenging when most people in the electrical industry still thought in terms of particle flow. I would need to develop new language and concepts for describing electrical phenomena, replacing the familiar hydraulic analogies with more accurate but less intuitive field descriptions. The social and professional implications were as daunting as the technical challenges. If I openly adopted field theory as the basis for my electrical work, I would be contradicting the established understanding of most electrical engineers. This could damage my credibility and reputation, particularly if my field-based designs failed to deliver the promised improvements. Yet the alternative was equally troubling. Continuing to work with known misconceptions felt intellectually dishonest and potentially limiting. How many opportunities for innovation was I missing by clinging to incorrect theoretical foundations? How much better could my electrical systems become if I designed them based on accurate understanding of electromagnetic phenomena? The question became not whether to embrace field theory, but how to make the transition safely and effectively. I needed to develop field-based design methods that clearly outperformed traditional approaches, demonstrating the practical value of more accurate theoretical understanding. This would require extensive experimental work, mathematical analysis, and careful testing of new design concepts. I would need to train myself and my assistants to think in terms of electromagnetic fields rather than mechanical flows. The process would be lengthy and demanding, but potentially revolutionary for the future of electrical engineering. The Pearl Street Power Station continued operating successfully throughout this period of theoretical upheaval. Customers received reliable electrical service without any indication of the conceptual crisis affecting my understanding of the underlying technology. But I knew that this apparent stability was based on incomplete knowledge that could limit future progress. Standing in my laboratory on cold winter evenings, surrounded by the familiar apparatus of electrical experimentation, I realized that I had reached a crossroads. I could continue working with traditional methods that were practically adequate but theoretically wrong, or I could invest in learning to design electrical systems based on electromagnetic field theory. The decision would determine not only my personal understanding of electrical phenomena, but also the direction of my future inventions and the legacy of my work in electrical engineering. Everything I had accomplished was based on partial knowledge. Everything I might accomplish in the future depended on whether I could master the true nature of electromagnetic energy transfer. The breakthrough came not through complex mathematics or sophisticated laboratory equipment, but through the most ordinary demonstration imaginable. A simple battery connected to a single incandescent bulb through two copper wires, the kind of circuit I had built thousands of times before. But this time, I observed it with fresh eyes informed by months of struggle with electromagnetic field theory. Spring had arrived at Menlo Park, bringing longer days and warmer temperatures to the laboratory. The improved lighting helped me see details that winter's dimness had obscured. I positioned the simple circuit on my workbench and studied it methodically, trying to perceive what was actually happening when electrical energy traveled from the battery to the light bulb. The conventional description was familiar and comfortable. Chemical reactions in the battery created electrical current that flowed through one wire to the bulb filament, passed through the filament while heating it to incandescence, then returned to the battery through the second wire. Simple, mechanical, easy to visualize, and completely wrong. I forced myself to observe this circuit through the lens of Maxwell's field theory, imagining the electromagnetic field that surrounded and permeated the entire arrangement. When I connected the battery to the bulb, I was not creating a flow of particles through the wires. Instead, I was establishing a field configuration that could support energy propagation from the battery to the filament. The battery served as a source of electromagnetic field energy, maintaining electrical and magnetic field patterns around the circuit. The copper wires acted as guides for field propagation, channeling electromagnetic waves from the source to the load. The bulb filament consumed field energy, converting electromagnetic waves into heat and light. This field-based description explained every aspect of circuit behavior that had puzzled me using the particle flow model. The instantaneous response occurred because electromagnetic field changes propagated at nearly the speed of light. The energy appeared simultaneously throughout the circuit because field effects were not constrained by slow particle motion. The circuit worked as an integrated electromagnetic system, not as a mechanical pipeline for moving electrical substance. More importantly, this understanding revealed why my previous design approaches had been suboptimal. I had been optimizing for particle flow when I should have been optimizing for field propagation. The difference was subtle but significant, affecting everything from conductor sizing to circuit layout to device positioning. I began redesigning basic circuit elements based on electromagnetic field principles rather than hydraulic analogies. Instead of making conductors larger to carry more current, I shaped them to support more efficient field propagation. Instead of arranging components for convenient mechanical assembly, I positioned them to minimize electromagnetic interference and maximize energy transfer efficiency. The results were immediately apparent. Circuits designed for optimal field propagation consumed less power, generated less waste heat, and operated more reliably than equivalent circuits designed using traditional methods. The improvements were not dramatic, but they were consistent and measurable across many different applications. Francis Upton was delighted by these practical confirmations of field theory. You see, Mr. Edison, Maxwell's equations are not merely abstract mathematics. They describe the actual mechanism by which your inventions function. Understanding this mechanism allows us to design better devices. His enthusiasm was infectious, but I remained cautious about embracing field theory completely. The improvements I observed were encouraging, but I needed to understand them more thoroughly before committing my business to fundamentally new design approaches. Revolutionary changes in engineering practice required extensive validation and careful risk management. I spent several months systematically comparing field-based and traditional designs across my full range of electrical products. Generators, distribution systems, lighting fixtures, control devices, measurement instruments. In every category, field-optimized designs showed measurable advantages over mechanically optimized equivalents. The generator improvements were particularly significant. By shaping the magnetic field configuration for optimal electromagnetic wave generation rather than maximum mechanical force transfer, I achieved higher efficiency and better voltage regulation. The electromagnetic approach revealed design possibilities that mechanical thinking had never suggested. Power distribution systems also benefited from field-based optimization. Traditional designs focused on minimizing resistance to particle flow, using thick conductors and short runs wherever possible. Field-based designs considered impedance matching, wave reflection, and electromagnetic coupling between parallel conductors. The result was more efficient power transfer with reduced losses and improved stability. Even simple lighting fixtures performed better when designed for optimal field interaction with the electrical supply system. By controlling the electromagnetic environment around the bulbs, I could extend filament life, improve light quality, and reduce power consumption. These improvements accumulated to significant practical and economic benefits. The evidence was overwhelming. Electromagnetic field theory provided a more accurate and more useful description of electrical phenomena than the traditional particle flow model. Devices designed using field principles outperformed devices designed using hydraulic analogies. The theoretical investment was paying practical dividends. But the most profound realization was not about device performance. It was about the elegant simplicity of electromagnetic field propagation compared to the artificial complexity of particle flow explanations. The field model unified electrical and magnetic phenomena into a single coherent framework, while the traditional model required separate and sometimes contradictory explanations for different aspects of electrical behavior. Consider the simple battery and bulb circuit that had triggered my breakthrough understanding. The particle flow model required explaining how electrical particles moved from the battery through the first wire, passed through the bulb filament, traveled through the second wire, and returned to the battery. Each step involved different mechanisms and raised different questions about the nature of electrical current. The field model offered a unified explanation. The battery maintained an electromagnetic field pattern that extended throughout the circuit. Energy propagated from the battery to the bulb through this field, traveling as electromagnetic waves guided by the copper conductors. The bulb filament intercepted the field energy and converted it to heat and light. No particles traveled from source to load, only field waves carrying energy. This field-based understanding eliminated many conceptual difficulties that had troubled me for years. Why did circuits respond instantly? Because field propagation was nearly instantaneous. Why did electrical energy appear throughout the circuit simultaneously? Because the field extended throughout the circuit from the moment of connection. Why did conductor properties affect circuit performance in complex ways? Because conductors guided and shaped field propagation, not particle flow. The transition from particle thinking to field thinking required abandoning deeply ingrained mental habits. I had spent decades visualizing electrical current as something substantial moving through wires, like water flowing through pipes, learning to think in terms of invisible field waves propagating around and through circuit components demanded constant conscious effort. But the rewards justified the difficulty. Field-based thinking revealed design opportunities that mechanical analogies could never suggest. It explained electrical phenomena that particle models could only describe through arbitrary assumptions. Most importantly, it provided a foundation for systematic improvement of electrical systems based on accurate understanding of underlying physical mechanisms. My confidence in field theory solidified as I applied it to increasingly complex electrical problems. Large power distribution networks, multi-phase generator systems, parallel circuit configurations, electromagnetic interference issues. In every case, field-based analysis provided clearer insight and more effective solutions than traditional approaches. The business implications became apparent as my field-optimized designs outperformed competing products in the marketplace. Customers noticed the improved reliability, efficiency, and performance of systems designed using electromagnetic principles. Word spread throughout the electrical industry about the superior characteristics of Edison systems, though few competitors understood the theoretical foundations responsible for these improvements. I began incorporating field theory concepts into my patents and technical publications, describing electrical devices in terms of electromagnetic field interactions rather than particle flow. This language was unfamiliar to most readers, but it accurately captured the true mechanisms underlying device operation. The transformation of my understanding was profound and permanent. I could no longer think about electrical phenomena in terms of particle flow, even when communicating with colleagues who had not yet encountered field theory. The electromagnetic perspective had become my natural way of perceiving and analyzing electrical systems. Standing in my laboratory on warm spring evenings, surrounded by electrical devices that I now understood in fundamentally new ways, I reflected on the journey from mechanical intuition to field-based insight. The transition had been difficult and sometimes unsettling, challenging assumptions that had guided my work for decades. But the result was immensely satisfying. I finally understood what electricity actually was, not merely how to manipulate it for practical purposes. The mysterious instantaneous responses that had puzzled me for years now made perfect sense as natural consequences of electromagnetic field propagation. More importantly, this accurate understanding opened possibilities for innovation that had been invisible when I worked with incorrect theoretical foundations. Every electrical device could potentially be improved by optimizing for field propagation rather than particle flow. Every system could benefit from electromagnetic design principles rather than hydraulic analogies. The simple battery and bulb circuit remained on my workbench as a reminder of the breakthrough that had transformed my understanding. Such an ordinary arrangement, yet it had revealed the true nature of electrical energy transfer when observed with proper theoretical perspective. Sometimes the most profound discoveries emerge from the most familiar phenomena, viewed with fresh eyes informed by deeper knowledge. The leather-bound notebook sits before me now, 30 years after I first began recording my investigations into the true nature of electrical phenomena. Its pages chronicle the transformation of my understanding from simple mechanical analogies to sophisticated electromagnetic field theory. More importantly, they document how this knowledge revolutionized every aspect of my electrical engineering practice. Those early entries, written in the uncertain hand of someone grappling with concepts that challenged everything he thought he knew, seem almost quaint now. Measured electron velocity today only millimeters per second. How can this be correct? The question mark after that statement captures perfectly the intellectual crisis that drove my investigation forward. Later entries show growing confidence as field-based explanations proved their practical value. Generator efficiency improved 12% using field optimization principles. Filament life extended significantly with electromagnetic coupling considerations. Distribution system losses reduced through impedance matching based on wave propagation theory. Each success strengthened my conviction that electromagnetic field theory was not merely abstract mathematics, but the key to superior electrical engineering. The business impact of this theoretical revolution exceeded my most optimistic expectations. Edison Electric Light Company became the dominant force in electrical power generation and distribution, largely because our systems outperformed competing designs that relied on outdated particle flow concepts. Customers experienced fewer failures, lower operating costs, and better service reliability with equipment designed using electromagnetic principles. My competitors struggled to match the performance of field-optimized Edison systems. Without understanding the theoretical foundation for our design advantages, they could only copy superficial features while missing the electromagnetic principles that made those features effective. This technological leadership translated directly into market dominance and financial success. But the most satisfying aspect of this transformation was not commercial success, but rather the intellectual clarity that came from understanding electrical phenomena accurately. Every circuit, every device, every system now made perfect sense as manifestations of electromagnetic field interactions. The mysterious instantaneous responses that had puzzled me for decades became natural consequences of near light-speed field propagation. This clarity eliminated much of the trial-and-error experimentation that had characterized my earlier work. Instead of testing numerous mechanical variations to achieve desired electrical behavior, I could now predict optimal configurations using electromagnetic field analysis. The design process became more efficient, more systematic, and more reliable. Training my assistants in field-based thinking proved more challenging than I had anticipated. Engineers and technicians, with years of experience using hydraulic analogies, found it difficult to abandon familiar mental models. in favor of abstract field concepts. Some never made the transition completely, continuing to describe electrical phenomena in terms of particle flow while applying field-based design principles mechanically. Francis Upton emerged as my most effective teacher of electromagnetic theory to new employees. His mathematical background allowed him to present field concepts in rigorous yet accessible ways. Under his guidance, younger engineers learned to think electromagnetically from the beginning, without the burden of unlearning mechanical misconceptions. The electrical industry as a whole was slower to adopt field-based understanding. Most engineers continued using particle flow language and hydraulic analogies well into the 20th century, even as they unconsciously applied design principles that only made sense from an electromagnetic perspective. The gap between practical success and theoretical understanding persisted throughout my career. This disconnect frustrated me, particularly when explaining electrical phenomena to investors, customers, and journalists. How could I describe the true elegance of electromagnetic energy transfer to audiences that thought in terms of mysterious electrical fluid flowing through wires? The language of field theory was precise but intimidating. The language of particle flow was familiar but wrong. I developed a compromise approach, using mechanical analogies to introduce electrical concepts while gradually revealing the electromagnetic reality underlying those analogies. Electrical current behaves like water flow in some ways, but the actual mechanism involves invisible fields that surround the conductors. This transition strategy worked reasonably well for technical audiences, though it never fully satisfied my desire for complete accuracy. The public understanding of electricity remained stubbornly mechanical throughout my lifetime. Newspaper articles described electrical current as racing through wires at tremendous speed, carrying power from generators to homes and businesses. Textbooks explained circuits using water flow diagrams that reinforced incorrect mental models. Popular science books perpetuated the myth of electrical particles streaming through conductors. This widespread misconception had practical consequences for electrical safety and efficiency. People who misunderstood the true nature of electrical energy transfer made poor decisions about wiring, grounding, and device operation. Unnecessary accidents occurred because users relied on incorrect mental models when working with electrical systems. I tried to address these problems through my writings and public presentations, emphasizing electromagnetic field concepts whenever possible. But the challenge of translating abstract field theory into accessible language remained formidable. Most people preferred simple mechanical explanations, even when those explanations were demonstrably wrong. The irony was that electromagnetic field theory, once properly understood, was actually simpler and more elegant than particle flow models. Field propagation explained electrical phenomena through a single unified mechanism, while mechanical models required complex and sometimes contradictory assumptions about electrical particle behavior. Consider again the basic battery and bulb circuit that had triggered my breakthrough understanding. The electromagnetic explanation was straightforward. The battery maintained a field configuration that supported energy wave propagation to the bulb, where the waves were absorbed and converted to heat and light. Clean, simple, complete. The particle explanation required multiple assumptions. Electrical particles somehow moved from battery to bulb, passed through the filament while transferring energy through an unspecified mechanism, then returned to the battery by an equally mysterious process. Each step raised questions that could only be answered through additional assumptions. Yet most people found the particle explanation more intuitive because it resembled familiar mechanical processes like water flowing through pipes. The field explanation seemed abstract and difficult despite its fundamental simplicity and accuracy. This preference for mechanical over electromagnetic thinking reflected deeper patterns in human cognition and education. People learned physics through mechanical examples before encountering electromagnetic phenomena. They developed strong intuitions about solid objects and fluid flows before studying invisible fields and energy waves. The sequence of learning created mental frameworks that were hard to modify later. My own experience confirmed this educational challenge. Despite overwhelming evidence for electromagnetic field theory, I occasionally found myself reverting to mechanical language when discussing electrical problems informally. The particle flow model was so deeply embedded in electrical engineering culture that it influenced even those who knew it was wrong. But the practical benefits of electromagnetic thinking were too significant to ignore. Every major advance in electrical technology during my career resulted from applying field theory rather than mechanical analogies. Power generation, distribution, lighting, communications, measurement, control, all benefited from electromagnetic design principles. The students and young engineers who learned electromagnetic thinking from the beginning, without the burden of mechanical preconceptions, consistently outperformed their more experienced colleagues who remained trapped by particle flow models. This generational transition gave me confidence that field-based understanding would eventually become dominant in electrical engineering. Looking back on this intellectual journey, I am struck by how much my investigation was driven by simple curiosity about apparently minor discrepancies between theory and observation. The slow electron velocity measurements that triggered my field theory exploration seemed like technical details with little practical significance. Yet they led to revolutionary improvements in electrical system design and performance. This experience taught me the importance of investigating anomalies thoroughly, even when they appear unimportant. Nature often reveals her deepest secrets through small inconsistencies that challenge our assumptions about how things work. The most profound discoveries emerge from careful attention to phenomena that don't quite fit established patterns. The transformation of my understanding also demonstrated the practical value of accurate theoretical foundations for engineering work. Electromagnetic field theory was not merely academic speculation divorced from real-world applications. It was a precise description of natural phenomena that enabled superior technological solutions. Engineers who dismiss theory as impractical abstraction are making a costly mistake. Theory is simply organized knowledge about how the world actually works. Accurate theory leads to effective practice. Inaccurate theory leads to suboptimal results. The choice between theoretical rigor and practical success is false. The most practical approach is to base engineering work on accurate understanding of underlying physical mechanisms. My leather notebook, now filled with 30 years of electromagnetic insights and applications, represents more than personal intellectual development. It documents the transition from one era of electrical understanding to another, from mechanical analogies to field theory, from approximate descriptions to accurate explanations. The electrical devices that surround us today operate according to electromagnetic principles that I helped establish through systematic investigation and practical application. Every light bulb, every electric motor, every power distribution system embodies the field-based understanding that emerged from my simple measurements of electron velocity in copper wires. Most people who use these devices daily remain unaware of the electromagnetic reality underlying their operation. They continue thinking in terms of electrical current flowing through wires, perpetuating misconceptions that I abandoned decades ago. But the devices work properly because they were designed by engineers who understood electromagnetic field propagation, regardless of the language they used to describe their work. This is perhaps the most important lesson from my investigation into the true nature of electricity. Accurate understanding enables superior results, even when that understanding is not widely shared or properly communicated. The electromagnetic principles that revolutionize my electrical engineering practice continue to guide technological development, whether or not people recognize their fundamental importance. The truth about electricity remains as elegant and powerful today as when I first grasped it through careful observation and rigorous analysis. Electromagnetic fields carry energy at nearly the speed of light, enabling the instantaneous electrical effects that define modern civilization. Understanding this reality transforms how we design, build, and use electrical technology. The secret was never really secret. It was simply hidden beneath layers of familiar but incorrect assumptions that most people never thought to question.